What besides that?
Okay. All right. Section 4.2.
Yeah.
Has all to do with area under the curve.
Yeah.
And I'm not particularly fond of the way this book handles it.
I didn't quite understand it.
Well, that's what I'm not fond of, is they make it very difficult. They try to explain it in terms of sigma summations. And that's not the best way to understand it. If you're trying to learn to ski, you start on the beginner slopes and progress to the expert slopes. You don't start out on the expert slopes. So, let's talk about an easier way to look at it, and then we'll address the sigma notation. Let's talk about left ram, mid ram, and right ram. What I've drawn here is the curve f of x equals x squared plus 1. It's the standard parabola vertically shifted up by 1. Left ram. Left ram stands for left rectangular approximation method. The reason it's got the L is because the left of each rectangle is the function. In other words, that point right there is the left of that rectangle 1. That point right there is the left side of rectangle 2, and so forth.
Okay, that makes sense.
Okay, now the most important thing to understand here is we're going to sum up the area of these three rectangles to approximate the area under this curve. Well,
Okay.
What is the area of rectangle number 1?
1
Because the height is what?
is 1.
It's f of 1.
Yeah.
That's the key thing to understand. The height of the rectangle is not y, it's not f of x, it's f of 0. My mistake, big mistake. In other words, this point right here is f of 0, which happens to be equal to 1. When I plug 0 into the function, I get 1. So the area of this rectangle is 1. What is the area of rectangle number 2?
That would be 2.
Well, it's going to be f of 2, right?
Yeah.
In other words, this point right here, which is this point right there, is f of 2.
Oh, yeah. At f of 2, then it's 5. Well, no, 5 times 2.
I'm sorry. I'm sorry. I keep making mistakes. I don't know what I'm doing here. That point is f of 1. Here's 1 right here. So the y value at this point right here, which is right there, is f of 1. And f of 1 equals 2. In other words, when I plug 1 in for here, I get 2. So the area of this rectangle is a height of 2, a base of 1. So it's area 2 also. Rectangle number 3, what is its height in terms of f?
That would be f of 2, correct?
And that is 5.
5.
Its width is 1, so this area is 5. So the area under that curve by left ram approximation is 8. We can also see that when we use only 3 rectangles and we use left ram, there's all this area here that we're not accounting for. which means our approximation is going to be less than the true area. You with me?
Yeah.
So let's try a different method, which would be right RAM. Well,
so the right side of the rectangle touches the function?
yeah, here exactly. The right side of the rectangle touches the function. So the first rectangle is going to be that. Second rectangle is going to be that. And the third rectangle is going to be that. So the area of rectangle 1 using right RAM is 1 times what?
1 times, that would be f of 1, so that's 1 times 2.
Perfect. So that's 2. This rectangle here, what's its area going to be?
That rectangle is f of 2, so that would be 5 times 1, so 5.
And the third one?
Is f of 3, so that would be 10.
So with right RAM, we get 2 plus 5 plus 10, 17, a significantly different approximation, but that would be expected because all of this area is above the curve. So we would expect to be more. Well, there's a third method that generally is more accurate. In other words, the fact that left RAM under-approximated this curve would because the curve was concave up. If it had been concave down, left RAM would have over-approximated it, and right RAM would have under-approximated it. So you can't always say which will do a better job. It depends on the shape of the curve. A third method would be mid-RAM, which seems like it should always be a little bit better. That's where the midpoint of the curve when I say midpoint, I mean this midpoint.
Yeah.
So the first rectangle has an area of what? 1 times...
Is that a f of 0.5?
Yes.
So that would be 0.5 squared, which is 1.25.
Uh-huh. And the second rectangle would have an area of
1.5 squared.
2.25, that's 3.25. And the third rectangle would be f of 2.5, which is 6.25, 7.25. This is 11.75. Far more likely to be the accurate measurement of this thing, because we've got a little bit extra area there, but it's kind of compensated for. No, this still going to over-approximate it by this amount.
Yeah.
Okay? But that, in a nutshell, is left RAM, mid RAM, and right RAM. Now, in future chapters, you'll learn that a better way to approximate it is if I use trapezoids instead of rectangles. In other words, if I made my first thing a trapezoid like that, and my second one, instead of rectangles, I'm going to use trapezoids. You can see the trapezoids is going to be a lot more accurate than rectangles were. And what's the area of a trapezoid? It's 1/2 base 1 plus base 2 times height. So this very first trapezoid there would have an area of what? 1/2 base 1 is f of, this is base 1 right there, that's base 2 right there, and the height is this distance here.
So base 1 is f of 0, which is 1. And then base 2 is f of 1, which is, 2 times the height of 1.
Yes. The important concept is that you recognize that this point is f of 0, this point is f of 1, this point is f of 2, and this point is f of 3. Now you can approximate the area under any curve, no matter what the function is, with 4 different methods: left ram, mid ram, right ram, and trapezoid. Now you have to do it manually at this point, but that's okay. That you understand the concept. So let's look at your papers that I'd rather not start with this page here, just because that gets more into the summation. And let's put off 1 and 2 for just a moment. Let's continue on with this concept of left ram, right ram, mid ram on questions 3, 4, and 5, and then if we have time we'll go back and we'll talk about sums and sigma notation, which is the complicated part. That's the part that makes it seem complicated. Okay, if a truck moves with positive velocity from time 3 to time 15, the area under the graph of v of t between time 3 and time 15 gives what? In other words, there's the velocity curve. That is v of t. Wow, what did I do? Somehow. Oh gosh. All right. That is v of t. This is t. Let's see if I can get my black back here. There we go. All right. So if this is the velocity curve, the area under this curve would represent the total distance traveled. Why? because there's the position function. That's the position of a particle at any point in time. Well, the first derivative of that particle equals velocity, which means velocity equals the integral. In other words, if I take the integral of the velocity function, I get the position. So taking the integral of the velocity function is the same thing as finding the area under the curve. That's what integration means, is you find the area under the curve. So if I take the integral of the velocity function, I get the position function. So when I look at the area under this curve, I'm looking at the total distance traveled.
Yeah, that makes, I think I understand.
Okay. Let me give a more straightforward explanation of it. Let's say we travel at 60 miles an hour. This is the velocity function. And we go for 3 hours. Well, from hour 1 to hour 3, that's 2 hours. At 60 miles an hour, we're going to go 120 miles. It's the area under that curve. Notice that's a rectangle. We don't need calculus to figure that out. We can use geometry. It's got a base of 2, a height of 60. That area under that curve is 120 miles. So when you have a velocity function, if you can find the area under the curve, which is the same thing as taking the integral or antiderivative, then you're going to get the total distance traveled, the total displacement.
Makes sense.
Okay. So the answer here would be the distance traveled by the truck from t equals 3 to t equals 15.
Okay.
Now let's look at 4. Let me graph this on Wolfram alpha. It's 2x minus x squared. Okay. Now I'm going to draw it. There's a reason I use f of x and not y. When you use y, you can't say y of 1 or y of 2. And the concept of saying f of 1 or f of 2 is gigantic in calculus. So you want to start thinking of functions as f of x, because then you can evaluate that function at any x you choose. So divide it into 4 intervals. And partition it and do left ram. So tell me what the area under this curve would be using left ram.
So for left ram, the first one, we go up, and we
I'm going to
have
call it rectangle number 1 area equals what?
So for rectangle number 1, is that the function at 1/2?
If you use left ram, where is the left of end of this rectangle going to be?
The left end of that rectangle.
Let's take the second rectangle.
Oh, it's going to be at... So since the second rectangle... So the first rectangle falls at... I don't know. 0? Just 0?
In other words, the top of the left rectangle is right there. What about rectangle number 2? What is the area of that?
Rectangle number 2 hits the function at 1/2, so then we go 2x, so that's 1 plus 1/2 squared is 2.25. Oh no, not, it's minus, not plus.
Oopsie. F of 1/2
F is 1 minus
is 1
so that's 0.75.
1/4, 0.75. So F of 1/2 is equal to 0.75, and the width is only a half now, not 1. So the area of that is 0.375.
That's small. Then the next one hits the curve at 1.
So the area of rectangle 3,
2 minus 1 is 1, and then 1 times 1/2 is 0.5.
yes. And finally, rectangle 4.
Which hits the curve at 1 and 1/2, which is 2 times 1 and 1/2 is 3. 1 and 1/2 squared is 2.25, so that's 0.75. So that's 0.375 again?
Which makes sense. There's a certain symmetry here we can see.
Yeah.
Okay. So the sum of the left rams would be 1 1/4?
Well, yeah. That's what I got.
Okay. Now let's do right rams. So the first triangle, the first rectangle is that. So the area of
So then we would be, yeah, that's just 0.375.
okay, same as the area 2, or the same as the area of rectangle 2 in the other method.
Yes.
Okay.
And then
Means this one must be
0.5.
0.5. And this one's got to be, I think it's got to be the same as rectangle 1, doesn't it? Let's see. We're using right rectangles, so it's 3/2. This was 2x minus x squared. 3/2 is 3 minus 9/4. That's
should be
0.75. Huh.
And then times the 0.5.
Ah, there we go.
Yeah.
There we go. And this rectangle over here, which uses right ram,
Is 0.
is 0.
So we got the same for right
we
and
got
left.
the same. Yeah. And now let's do mid.
Mid.
Mid ram. So I'm not even going to look at the curve. Let's just go through the algebra. Rectangle 1, area is f of what times 0.5?
Since it's mid, is that f of 1/4?
Uh-huh.
Which 1/4 times 2 is 1/2 minus 1/4 squared, which is 1/16. And we get
7:30 seconds. Whoops, that goes right there. Did I do that right? That's 8/16 minus 1/16 is 7/16 times a half, 7:30 seconds. Okay. So rectangle number 2, let's see, that was rectangle number 1, right there. Rectangle number 2 is going to look about right there. In other words, we want this point to be the midpoint of that right there. So the height is f of 3/4. Width is 0.5.
and at f of 3/4 we get 6/4 minus 3/4 squared, which is 9/16.
15/16 times half, 15/30 seconds. Area of rectangle 3 should be the same, right? In other words, this should be exactly the same rectangle. We have complete symmetry about the x equal 1. In other words, if we look at this graph, you'll notice that the axis of symmetry is 1. So that rectangle has to be the same. So this has to be 15/30 seconds also, and the fourth one has to be the same as the first one. So it has to be 7/30 seconds. So what is that? 30 seconds plus 14 seconds, 44 seconds is the area using mid-ram.
44 seconds.
And that almost certainly a better approximation than either left ram or right ram.
Which is a little more than both of what we got for the other two. So that
yeah, and that makes sense because the other two figure to underestimate it. Okay, so that handles problem number 4. And I think you should now have an excellent understanding of how to approximate the area under a curve using rectangles.
Yeah, that makes sense.
Okay, good. Number 5. I don't want to spend our whole session on left, right, and mid rectangles because I think you get it now. But number 5, I could draw the function based on this table, right?
Yes.
In other words, let me just start a little bit of it. At 0, we're at 50. At 1, we're at 70. At 2, we're at 97. So even though we don't have a continuous smooth curve, we can still figure out the approximation using the rectangles, right?
Yeah.
And they want to use mid. So what is the area of rectangle number 1?
So rectangle number 1 is
What is f of 1/2?
half. F of 1/2. Like,
Best we can do is guess.
so is that like 60-ish?
Uh-huh. So the height of this rectangle is 60, its width is 1, so the area of this first rectangle is 60. What is the area of this second rectangle?
2, it's 1.5, so that's like 85-ish.
83.5. And so forth and so on for the rest of the problem.
Yeah.
So they want, notice that this leakage is a rate. Whenever you are given stuff that is a rate, you know you are looking at a first derivative. It's like velocity. If they give you a velocity graph, you're not looking at position, you're looking at the velocity, the rate of change. Well, this is a rate of change. It's leaking 50 gallons per hour at the start, but it increases as time goes by. By the 6th hour, we're leaking a huge amount, 369 gallons per hour. So when you want the total amount of oil that has escaped, you add up the area under that curve. And in this case, we're going to approximate it with mid-ram rectangles. And we did the first 2. So doing the rest of them is the same thing. But important concept is this rate. When you see something per hour or something per minute or something per second, you know you're looking at a rate and you're looking at a first derivative. Rate of change is the definition of first derivative, the instantaneous rate of change. In other words, when they measured this rate of change, at this instant it was 50 gallons per hour, but at this instant, an hour later, it was 70 gallons per hour. So what we're really talking about here is, it's called net change, integral as net change. In other words, if we know a rate of something and we want to know the total net change, we're going to integrate.
Okay.
A little bit of a complex example would be, let's say we have a beach that's constantly being eroded and we need a machine to add sand to that beach. Well, you don't add sand at a constant rate because sometimes the tides bring in sand, sometimes the tides take out sand. So let's say the rate of change of the sand is a function of sine minus cosine or some complicated function like that. And where depending on the time of day, the rate that the sand machine is pumping new sand onto the beach changes. So if I said, well, how much total sand has been pumped onto the beach in the first 5 hours based on this function, I'm going to integrate that function from 0 to 5, and that will tell me the total amount of sand that's been deposited on the beach. Same way that when we had the velocity function and we were trying to figure out what the total distance traveled was, that is the integral of this velocity function evaluated from 3 to 15. Now, this material is more from the next chapter, I think. Let's spend the last 20 minutes talking about these sigma sums, because this is where they really complicated matters.
Those made no sense at all. They just...
I know. I'm not surprised at all. I hated it when I saw that. I have 2 calculus books, and the hard one does it this way. The easy one starts out with left ram, mid ram, and right ram, and eventually touches on this method here. First of all, let's make sure we understand what this means. This is a 6-term sequence that we are going to add up all 6 terms of the sequence. That's what this means.
Okay.
What's the first term of the sequence?
A 1?
Well, it's when I is equal to 1. So 3 times 1 plus 2. There's the first term of the sequence. What's the second term of the sequence?
When I is equal to 2.
Okay. So what is that term?
So 3 times 2 is 6, plus 2 is 8.
Keep going.
Then we have 9 plus 2 is 11.
Keep
12
going.
plus 2 is 14. 15 plus 2 is 17. And 18 plus 2 is 20.
Add those up and you got the answer to the problem. Now, there is perhaps an easier way to look at this. I'm not convinced it's necessarily easier, but it's useful if I know that the sum of I, as I goes from 1 to n, is equal to n times n plus 1 over 2. That's just a formula they give you. So, in other words, I can use this formula to figure out this problem a lot quicker. Because I also know that the sum of 3i is the same as 3 times the sum of I. And that the sum of 3i plus 2 is the sum of 3i plus the sum of 2. So I can take my summation here. Let's first of all figure out what the sum of 3i would be.
So 3i. So we have 6
3 times n times n plus 1 over 2, where n is 6. So now I can just substitute 6 for that and 6 for that. So I have 3 times 6 times 7 divided by 2. That's 63. Which would be the sum of 3i as I goes from 1 to 6. Well, the sum of 2 going from 1 to 6 is just 6 times 2. So I would add 12 more for the sum of the 2 part, and 75. That's what that would total right there. 13 and 11 is 24, 38, 55, 75. So, in other words,
I can see how that'd be quicker.
Yeah, if I was going from 1 to 17, it'd be much faster to use that formula than it would be to count out each term of the series.
Yeah.
Incidentally, terminology, a sequence is just a bunch of numbers separated by commas. A series is a bunch of numbers that are added together. So when we're talking about adding stuff, which this sigma, that's what that means, adding, we're talking about a series, always. Now, your book gives you 4 formulas that are helpful. One was, I already gave it to you, I, which is equal to n times n plus 1 over 2, where I goes from 1 to n. Another very helpful one is what is I squared from 1 to n, and that ends up being n times n plus 1 times 2n plus 1 divided by 6. So, let's use the second identity to figure out make sure you understand what they mean here. I didn't mean the second identity, I actually meant the first identity, that identity. Let me erase the second one for a moment so we can look at the first one while we're doing this problem. If I wanted to know what the sum from I equals 1 to n of I plus 1 over n squared for n equals 10, 100, 1,000, those 3 numbers. Well, the important thing to know here is that for this problem, n is a constant. Because it's a constant, you cannot take variables outside of that sigma, but you can take constants. So if I choose to treat this in the following way, where I'm going to make it I goes from 1 to n, it's not easy to see why n is a constant here, but for the sake of argument, take my word for it. Then I can write it like that. And then I can write that as 1 over n squared times I from 1 to n plus 1 over n squared times 1 from 1 to n. In other words, is all I'm doing is the sum of A plus B is the sum of A plus the sum of B.
Okay.
Okay. And we know what that is. So I have 1 over n squared times n times n plus 1 over 2. So that is equal to that. And then the sum of 1 from 1 to n is just equal to n. Plus n.
Okay.
Okay? And that's another formula given to you, that the sum of C, which is a constant, where I goes from 1 to n, is just equal to n.
Okay.
Excuse me, it's actually equal to C times n. But in this case, C is 1.
Yeah.
In other words, if it was the sum of 5, it would be equal to 5n. So now we got that formula, and with a bit of distributing and finding common denominators, I end up with n plus 3 over 2n. So that's what I have, and they said evaluate it when n equals 10, 100, and 1,000. Well, so now I'm just going to plug in 10 for n. So when n equals 10, my sum is 13/20. When n equals 100, my sum is 103 over 200. You with me?
Yeah.
That's why n is a constant. Because n was a constant this whole time. That's the reason I was able to bring it out. And then when I come up with a sum of this in terms of n, I can evaluate it for various n. And that's what we did there. But in evaluating it, I used these formulas that are right at the beginning of section 4.2. I don't know if you have your book or not, but if you can turn to where the summation formulas are, theorem 4.2.
4.2. Let me see if that's...
It's actually theorem 4.2, and there's 4 summation formulas there.
She has all the pages and stuff in the book online, so I'm fine.
Ah, well, in my book, it's page 260. Does that get you a section? Yeah, summation formulas.
Yeah, she has it posted. It's not loading right now, but it is here.
Okay. Now, let's say that we wanted to know what the sum of this function was when n goes to infinity, because that's most series are infinite series. And as you get further into calculus, the C part of Calc BC has to do with infinite series. And so it's important that you understand a little bit about infinite series. Notice that when we solved this, we got n plus 3 over 2n. And we were asked to evaluate what this would be as n went to 10 or 100 or 1,000. What's the limit of this as n goes to infinity? Remember your limits?
Limits are the derivative.
Well, but there's a way to evaluate this limit without invoking derivatives. You're right, you could invoke L'Hopital's rule because we have infinity over infinity. We could take the derivative of the top and the derivative of the bottom. But try to remember, what's the limit of this as x goes to infinity?
As x goes to infinity.
In other words, the x's cancel out and you have 1/3. Okay, well, if I want to take the limit of this, I know that it's the ratio of the coefficients of the highest order variable. Or it's n over 2n plus 3 over 2n, and this clearly goes to 1/2, and this clearly goes to 0 as n goes to infinity. So the limit of that as n goes to infinity is 1/2 as n goes to infinity.
Oh, that's, yeah.
All right, let's look at your, all right, this part of this page here. Well, let's see. I think you can see what we're going to do here, right?
Yeah.
In other words, we're going to solve all these manually. We're going to start with k equals 5, come up with a number. We're going to add to it when k is equal to 6, 7, and 8. So this is going to have exactly 4 terms in it, and they're going to be all added together.
Yeah.
Same thing here, same thing there, same thing there, same thing there. We're not going to use those summation formulas. Well, we were able to use it on that one, but it's going to be harder to use on that one. We don't have a summation formula for 1 over k squared plus 1. We have a summation formula for this. What is number 5?
Number 5, c is a constant, right? So that's just 4 times c.
Yes, very good. That's the answer to number 5, is 4c. All right, let's look at number 7. I assume that your homework is to do these problems here?
It is, let me look. Yeah, it is, she has down 14, 17, 21, 23, and 30.
Okay. Well, let's start with something a little easier than 14. In other words, now we have to go backwards. We've just figured out what sigma means, and now they want us to write this series in sigma notation. Well, number 7, what's that look like? Any idea? I'll give you a hint. I is going to go from 1
to
what?
11.
Okay. And what's the series going to look like?
1 over 5i.
You got it. So the first term would be that, the next term would be that, so forth up to 11. About this one?
This one we have, it goes from 1 to 14,
The 9 stays the same.
and it's, 9 over 1 plus I.
Okay. Let's jump up. Let's take a look. Some of these look like they could be complicated, harder. We only have a few minutes. Let's see. Number 9 is pretty clear. Which number is changing by 1?
Yeah.
So number 9 would be 7i over 6 plus 5. Right?
Yes.
Okay, let's go to 14.
So,
What stays the same with every term?
the
Square root.
yeah, the square root is
So
staying the
let's start
same.
with that.
The 1n out front is staying the same. The 1 over n out front of the square
So
root.
that, I can actually put that out here.
The 1 minus underneath the square root is staying the same. It's 1 minus the quantity that's changing.
And I, in this case, is going from 0 to n, since they don't give us an n. In other words, in all these other problems, we had numbers.
Yeah.
We should have done 11 because it has an n in it. But that's okay. We've started with 14 here. Now, let's take this 1 over n and put it back inside like that. I'm a little more comfortable with that. But this appears to be what it is. Ooh, what's the problem with what I just did?
1 over I to the...
No, there is no problem with it. In other words, my first thought was, uh-oh, when I is 1, I'm going to be dividing by 0. But remember, it's I that's 0, not n.
Yeah.
N is actually a constant here. They just haven't told us what it is. N could be 11, N could be 14, N could be infinity. So N is a constant. Let's go ahead and remove it and put it out here. Now we've written it perfectly. The I is what advances from 0 to 1, and the last term is n minus 1. So if n was 15 instead of n, then our last term would be 1 minus 14 over 15 squared. In fact, if n was 15, everything would be written like this. You with me?
Yeah.
But they don't pin it down. They don't want to pin it down to 15. They want to leave it open. They want to leave n so that n can be anything we want it to be, and in which case, I didn't quite write this correctly here. Let's see. It's the square root of this right here, 1 minus n minus 1 over n This is I, not n, is the problem. I don't like that either. We've got to have our first term be 0. So does this work? Well, when I is 0, we have that term right there, regardless of what n is. The next term is I is 1.
That's what she got.
This is what she has?
Yeah.
Okay. All right. Well, hopefully I've helped you understand area under the curve and the beginning of series.
It makes more sense. Before I had no idea, and now I think I can do the homework.
Yeah, hopefully. Yeah, I hope so. Because I really don't like the way they do this chapter in this book. As much as I'm fond of this book, I actually like it a lot more than my other calculus book. But this is the one chapter that I really hated the way they addressed, just because it made it so complicated. All right, Chase, I will talk to you next Saturday at 2.
Okay. Talk to you later. Thank you.
You're welcome. Bye-bye.